Today we will solve the questions of the final exam of fall 2023. Let's start by the first question. In the first question, we have a positively charged particle is projected in first case anti-parallel to uniform electric field E, and in the second case anti-parallel to the uniform magnetic field B. Knowing that in both cases the particle continue moving along the same line, how does the speed change? So as you know, the electric field does work on a charged particle. So E does work on the charged particle. However, the magnetic field does no work. So what means does work and does not work? Does work means can affect the speed of the particle. And the electric field, as you know from chapter 21, can also change the direction of the particle. In our case, is anti-parallel. So that means our acceleration is in the same direction as the electric field, because as you know, the acceleration is QE over m. In our case, we have a proton positively charged particle, so the acceleration and the electric field will be in the same direction. Okay, so this is the direction of our acceleration. From the general physics one, you know that if the dot product between the acceleration and the velocity is negative, in this case, the particle is decelerating. Okay, the particle decelerates. So what we can say that the speed of the particle decreases when it's projected anti-parallel to the electric field and the charge of this particle is positive. What about the magnetic field? The magnetic field does no work, so that means the velocity is the same, stay the same in the case of the magnetic field. So the correct, what are the options? Stay constant in the electric field? No. Stay constant in the electric field? No. Decreases in the electric field and stay constant in the magnetic field? This is true. Why this is wrong? Increases in the electric field? This is wrong, increasing, because our acceleration is in the same direction as the electric field because the charge is positive, and the velocity is opposite to this direction of the acceleration. Let's move to the second question. In the second question, we have two infinitely large parallel plan plates of non-conductive material are positively charged with uniform surface density of charge sigma, and sigma is positive. The same for the two plates. Sigma is the same for the two plates. What is the magnitude of the electric field in the space between the two parallel plates? So let's take our point is here between the two plates. As you know, infinitely large plate produces an electric field equal sigma over 2 epsilon naught. In our case, sigma is positive, and let's denote the first plate by 1 and the second plate by 2. So let's say this is E1 and let's say this is E2. And both of them are sigma over 2 epsilon naught because the two plates are positively charged with the charge density sigma. So what we can say here, the first plate produces an electric field outward. Why it's outward? Because it's positively charged. The second plate produces an electric field also outward. Why? Because it's also positively charged. So we can see here that our total electric field is the superposition of the two fields. So, however, the two fields have the same magnitude but opposite direction. Same magnitude, opposite direction, their sum is 0. Okay, opposite direction but same magnitude. Let's continue. And the third question we have, the figure beside represents electric field lines in some region of the space. How to compare the electric potential VA at the point A and the electric potential VB at the point B. So as you know, the electric field lines always points from the higher potential to the lower potential. To memorize this, let's take, for example, two parallel plates. This is 5 volt and this is 0 volt. For example, here we have, this is our electric field in the case of two parallel plates. So what we can say that the electric field lines, the lines, always pointing from the higher potential to the lower potential. So what we can say about this potential, it's VA greater than VB. And the correct answer will be B also. Let's continue. In this question, question 4, concerns the capacitance of the capacitor. So the capacitance of the capacitor when the vacuum is between the two conductors is C naught. What is the capacitance of the same capacitor when a dielectric constant kappa fills the space between the two conductors? So as you know, when we insert a dielectric between the two parallel plates to fill the space between the two conductors, in this case, the capacitance increases by kappa. Why it's increasing? Because kappa is greater than 1. So if we multiply something with, if we multiply a number with a constant greater than 1, of course, it's going to be increasing. And the correct answer is A. Let's continue with question B, question 5. The flow of ions is composed of the same number of Na ion and Cl- ion. The two types of the ions are moving with the same speed and in the same direction. So they have the same speed and they have the same direction to the right. So what is the difference between these two situations? In the first situation, we have a charged particle with the plus charge, plus charge is moving to the right. And a negatively charged particle is moving to the right also. The difference is in the sign of the particle of the charge and the number of the charge also. Is the total current I created by this flow is 0? If not, what is the direction of the current I? So as you know, the current I follows, the conventional current I follows the positive charge direction. Okay, it follows the positive charge direction. So the current here in the first situation is to the right with the direction of the positive charge. And how many units we have? We have 2 units. 2 units of the current. Okay, what about the second case? The second case, the negative charge is moving to the right, so the current is opposite to the negative charge. And this is the direction of the current. And how many units we have? We have only 1 unit. What is the total current? It's only the sum. So what is the I total? Let's say this is I1 and let's say this is I2. I total is going to be I1 plus I2. So it's going to be 1 unit in which direction? It's in the direction to the right. Okay, so it's different to the 0 and directed to the right. Very good. Let's continue. Question 6. How does the resistivity of an ohmic material changes with increasing the temperature? As you know, the resistivity depends on the temperature for the ohmic material and follows this path. Okay, so this is the temperature and this is the resistivity. And what do we call this point? It's rho naught. Okay, so it's going to be rho naught factor of 1 plus alpha T minus T naught. And this is our equation of the resistivity dependence on the temperature. So as you know, it's increasing with the temperature, with the increase of the temperature. Let's continue. Now, question 7. N identical light bulbs of resistance R, each are connected in series and connected to the battery of the potential difference delta V. the internal resistance of the battery is neglected. The total light brightness produced by these bulbs is proportional to what? So as you know, the brightness is proportional to the power. And the power is equal VI, which is equal V squared over R, equivalent for the total brightness. Here he's talking about the total brightness. Okay, so let's say here it's delta V, okay, which is proportional to I squared multiplied by R equivalent. Okay, because we are talking about the total brightness. Okay, so all of them are connected in series. When different elements in the circuit are connected in series, they have the same, they are carried by the same current. So which equation we will use? Which equation we will use? They are carried by the same current. The same current travels through all the elements of the circuit. At first, what is R equivalent in our case? All of them are connected in series and they have identical light bulbs, so they have identical internal resistance, so it's going to be N multiplied by the resistance of one light bulb. Okay, so which equation we would use? All of them, this is delta V, all of them are connected in series and they carry the same current. So in this equation, the current will be the same, okay? In this equation also, the current is the same. In this equation, the current is the same. But we don't have any information about the current. Here in the options, there is no current. So only we have delta V and R, delta V and R, delta V and R. Of course, we have the number of light bulbs. So which equation? So we're going to use this equation. By substituting R equivalent by N multiplied by R, so we're going to get the brightness is proportional to the power, and the power is equal to delta V squared over N multiplied by R. N multiplied by R is R equivalent. So the correct answer is going to be delta V squared over NR. Let's continue to question 8. An electron and proton moving to the right enter a region of uniform magnetic field directed into the page. How does the path of each particle deflect in the magnetic field? So as we said, the deflection of the particle is the same direction of the force. And as you know, the force exerted by the magnetic field on a charged particle is Q V cross P. As we said before, we have two different situations. The first one, if the charge is positive, so F follows the right-hand rule. And I will explain what means the right-hand rule. In the second case, when Q is negative, F is opposite to the right-hand rule. The right-hand rule said, put your fingers in the direction of the vector V, because it's the first vector in the cross product. Curl your fingers toward the vector B, because it's the second vector in the cross product. And your thumb points in the direction of the cross product vector, which is nowadays F if Q is positive. So the charges are moving to the right. The magnetic field is into the page. So for the positive charge will be deflected upward. Okay, will be deflected upward. Sorry, here before, because the magnetic field starts from this region, so the deflection starts from here. And what about the negative charge? It's going to be opposite to the right-hand rule. The right-hand rule gives the force up. The charge is negative for the electron, so it's going to be down. Okay, and they are deflected with the same. Okay, so we are done with this question. Let's move to question 9. 6 infinite straight wires carry current of different values and different directions, as shown. The point is out of the page and the cross is into the page. What is the value of the line integral BDS along the closed path encircling the currents in the counterclockwise direction? Okay, so we recall that Ampere's law is the line integral of BDS equal mu naught multiplied by I enclosed. If we want to calculate the line integral and we don't have any information about the magnetic field, we can use mu naught multiplied by I enclosed. I enclosed means the sum of the current, the algebraic sum of the current enclosed by the path. This is our path, this is the direction, and we already have the sign of the current. But if we don't have the sign of the current, we can determine the sign of the current. How? Put your fingers in the direction of the path, and your thumb points toward the positive current, the direction of the path. So in our case, if it's counterclockwise, so the current out of the page is considered as positive. Okay, let's come back. I enclosed in our case, it's going to be 7I positive minus I and minus 2I. These currents and these currents are not considered because they are out of the path. So it's going to be a very long idealized solenoid has a length L and the diameter D is composed of N loops and carry a current I. Which parameter doesn't affect the magnetic field B created by the solenoid near its axis? That means outside. Keeping the other parameter fixed. As you know, the magnetic field produced by solenoid is equal mu naught, the number of turns divided by the length multiplied by the current. Or we can say mu naught small n I. This is the number of turns. This is the length. And this is the current. What do we call the small n? Is the number of turns per unit of the number of turns per unit. Okay, in our case, we want to discuss the magnetic field as a function of the current, as a function of the diameter, as a function of the number of turns or the loop and the length. From this equation, we can see that the magnetic field depends on the number of turns, depends on the length, and depends on the current. So which equation, which parameter does not affect the magnetic field? Of course, it's the diameter. Okay, so we are done. Thank you so much. Let's wait for the key answers of the second problem.